So looking at our radical sign again, we got to talk about our different parts of the radical, because I'm going to be using the vocabulary words for it. If you have a number out in front of the radical, and it's always just a small little written number, we refer to that as the index. That tells you what root we're trying to find. So if we have a 3 there, that means we're trying to find the third root or the cube root. What number multiplied 3 times gives you the answer underneath? If it's a 4, what number multiplied 4 times gets you the answer underneath? We call that answer underneath your radicand. So in our notation here, we refer to this as the nth root of k. So you're trying to find the nth root of k. Sometimes we call it the square root of k, cube root of k. But that's what we're trying to look for. So here, let's take a look at our first example. Example 1, we're trying to find the 5th root of 32. So first thing I would do is look on my little sheet that I gave you guys. Is 32 one of our perfect 5th roots? Yeah. So the 5th root of 32 would be 2. That means if I take 2 and I multiply it 5 times, I'm going to get 32. Now let's take a look at our 4th root. So is 81 one of our perfect 4th roots? What do we get? 3. And because of this negative out in front, our answer is going to be a negative 3. And then our third example, we have a negative 27. If you have an odd exponent, an odd root, I should say, you can have a negative underneath. If you have an even root and you have a negative underneath, that's going to get into something we're going to do either not next class, but the class after. That's going to get into something new. So I know 27 is a perfect cube. What would be the cube root of 27? 3. But because it's negative, that means my answer would just be negative 3. Like back here at example 1, if I wanted the 5th root of negative 32, that would be a negative 2. An odd root, I can actually take the root of it when it's negative. If you have fractions, what you want to do is just kind of separate it and then take the square root of the top, square root of the bottom. So for this one, I'd want to take the square root of x squared and the square root of 16 separately. I can do the square root of x squared because it's an even exponent. So what I do is I would just divide that by 2, so it becomes just x to the first. You always divide by whatever your index is. And then the square root of 16 would be a 4. So my answer for that one would be plus or minus x over 4. So our second example, again, we want to separate it. Square root of 25 over the square root of 9. So what would that give us as our answer? 5 over 3. And then our third example, we're doing a cube root. So we're doing the cube root of negative 8 over the cube root of 27. So again, it's an odd root, so it's okay to have the negative there. What would be our cube root of 8? Negative 2. And then cube root of 27 would be a 3. So negative 2/3. How are we doing with those ones so far? Coming back a little bit, we did do a little bit of simplifying radicals in 9th grade. Okay, so let's take a look at our examples down here. When you don't have perfect squares underneath your radical sign, if you recall, what we need to do is we need to separate it. Where in the first radical, we have to put a perfect square. And then in the second radical goes basically whatever is left once you take your perfect square out of there. So not only does that first radical have to be a perfect square, but it has to be the largest perfect square that goes into the number. So for example, for 72, There are actually 3 perfect squares that go into it. Yeah, only 3. 36 is the largest perfect square that goes into it, so we have to use the 36. A lot of people with 72, they right away say, oh, 9 and 8. And you would be right. 9 is a perfect square. 9 times 8 is 72, but 9 is not the largest, so that's why we don't use that one. So then the square root of 36 is a 6. I don't write the radical sign anymore because I've used it. When I take that square root, I've used that sign. I don't write it anymore. We cannot actually take the square root of 2 because it's some ugly, nasty decimal that just goes on forever. So we leave that as square root of 2. So we get 6 radical 2. Now, when we get variables underneath, we have to do the same process. We've got to find the largest perfect square out of the variable. That goes in the first radical. What's left goes in the second radical. So in this example, we're simply doing a square root. So you want to find the largest number that is either 7 or lower that can be divided by 2, if that makes sense. So like, for example, I can't divide 7 by 2. I'd get a decimal. I can't have that. But I can divide 6 by 2. So a to the 6 would be my perfect square. I would still have one more a left. So that a to the first would go in the other radical. Which, if you remember, if I were to multiply these back out to get up to here, I would add my exponent. So 6 plus 1, I still have all 7 of them. And then b to the 20th, that's already a perfect square because the 20 is an even exponent. So that one's good. So all of that one goes in the first radical. So we want to divide in the first parenthesis, divide by 2 since we're taking square roots. So 6 divided by 2 gives me a to the third. 20 divided by 2 gives me b to the 10th. And we still have that radical a afterwards. Try to make it a little bigger so you guys can see it a little better. We're going to practice those ones. The variables are a little tricky sometimes. All right, number 3, doing a third root. So we got to find the largest perfect cube that can go into 24. So if you look at your perfect cube list, what's the largest perfect cube that goes into 24? 8. 8 times what? So I put my 8 first, my 3 second, even though it's a cube root, it still follows the same process as our square root. So then our cube root of 8 is a 2. And then we still have this cube root of 3 afterwards. And you want to be careful when you're writing it because sometimes with this index, if you aren't too specific with it, it looks like it's an exponent on a 2 and not the cube root like you're trying to write. So you got to make sure you're careful with that. All right, so let's try example 4. Is 27 a perfect cube? Yes. So I'm going to put the 27 in the first radical. Looking at my x to the 8th, can I divide 8 by 3 and get an integer? No, I'd get a decimal. So I could divide 6, though, by 3, and that would work. And then in my other radical, I would put my other 2 x's. And then how about y to the third? Yeah, I can divide 3 by 3. So y to the third is a perfect cube. So that one stays up front. So then what is the cube root of 27? 3. Again, you divide your exponents by the index. So we're dividing by 3. So this turns into x squared. And that would be y to the first. But we don't have to write that one. And then we still have the cube root of x squared. All right, we got one more. Try to make it bigger. we're going to keep our 2x squared y. That's going to stay out in the front. And then we set up our two radical signs. There is no little number written, so that's your hint that it's a square root. We don't always write the 2 when it's a square root. The other ones we always have to write. So the largest perfect square that goes into 50, 25. And then it's 25 times 2. X to the 7th is not a perfect square because, again, we cannot divide 7 by 2. However, we can divide 6 by 2. So then you would have x to the 1st in the other one. And then how about our y's? Yeah, y to the 10th. I can divide 10 by 2. So I get y to the 10th in there. So I still have this 2x squared y that was out in front. And then it's going to be times, square root of 25 is 5. Divide our exponents, so I get x to the 3rd, y to the 5th, and then the square root of 2x. And now we just need to multiply our things out in front. 2 times 5 gives us a 10. X squared times x to the 3rd would be x to the 5th. Remember, when we're multiplying like that, we add our exponent. Y to the 1st times y to the 5th. Y to the 6th. And then we got our square root of 2. So that one is our final answer. So until you get the hang of these, sometimes you just got to go nice and slow through them. And then you'll start getting faster and faster. So then what's going to happen is sometimes you're going to have to add your radicals, subtract your radicals, multiply them or divide them. So when you are adding radicals, you can only add like terms, which means you have the same radicand and the same index. So meaning it's got to be the same kind of root, whether it's square root, cube root, fourth root, that has to be the same. And the number underneath has to be the same. So if I look at our first example, my radicands are not the same. I can't do anything yet. So what we need to do is simplify them and then see if we can add anything together. So looking at the 27, what's our largest perfect square that can go into 27? 9. So it would be 9 times 3. Square root of 9 is a 3. And remember, we have to do that 3 times the 5 that was already out in front. So completely simplified. That one gives me a 15 radical 3. Can we simplify our 4 radical 3 anymore? No, so I'm just going to bring that one down. Coming after my 15, so I have 15 radical 3 minus 4 radical 3. 12, however, we can simplify that one further. So I'm going to set up my 2 and then my 2 square root sign. What's our perfect square that goes into 12? 4 and 3. This is another one. A lot of people give me a different number. A lot of people like to tell me 6 and 2, which is right. Yeah, 6 times 2 does give you a 12, but neither of those are perfect squares. You always got to remember to have your perfect square in there. 4 comes out as a 2, but then I have to do it times the 2 that was already there. So then that gives us a 4 radical 3, so I add that to the end, 15 radical 3 minus 4 radical 3 plus 4 radical 3. So now that I have the same radicand and all my radicals, they're all a radical 3, you add and subtract your numbers out in front just like you would for an x. So 15 minus 4 would be 11, plus 4 brings me back up to 15 radical 3. So just like when you add your like terms with your x's, your x itself doesn't change, just the numbers in front do. Alright, so example 2, subtraction. Numbers underneath are not the same, so we need to make them the same first. So for the first one, I'm going to set up my 2 square root signs. The largest perfect square that goes into 18, 9 and 2. So then how would we separate our x cubed? Which one would go in the first radical? X squared, yep. And then we would just have x to the first in our second radical. Again, when you add your exponents, you still have all 3 that we started with. Square root of 9 is 3. Square root of x squared is x. But I have to multiply it times the 5x that was already there. So after we multiply, what do we get? 15x squared, radical 2x. Alright, let's try the next one. So 72 and then x to the 5th. Again, 72, I like to use this one over and over again to make sure it drills into your head which one we use for 72. What's our largest perfect square? 36. 36 and 2. So then we have an x to the 5th. So we're going to put x to the what power in the first radical? 4th, yep. X to the 4th and then x to the 1st. So then I'm going to take my square roots. This gives me 6x squared, radical 2x. And then I just bring that down, line it all up, because there's nothing to multiply times in that one. So now we can subtract 15x squared minus 6x squared would give us 9x squared radical 2x. Again, radical stays the same. You're just adding and subtracting the numbers out in front. Yes, ma'am. Well, you're subtracting the coefficients of the x squared. Because if I had, like, let's say 15x squared radical 2 minus 9x radical 2, I wouldn't be able to actually subtract those because those aren't like terms. So my final answer on that one, I would have to put parentheses radical 2. Because you can't actually subtract them. Alright? Okay. Multiplying radicals, you want to actually multiply them first, simplify after. I have a lot of people who try to simplify first, then multiply, and then you simplify again. So you're just kind of creating more work for yourself. So you want to multiply them first, simplify after. When we multiply, again, it's very similar to when you multiply your x's. You multiply your coefficients, multiply your numbers out in front first. So negative 2 times 3 would give us a negative 6. Oh, because Rebecca was asking me a question, I answered it. So multiply numbers in front, and then you multiply the numbers underneath. So 3 times 6 gives me an 18. And now we have to go and simplify. So again, what's the largest perfect square that goes into 18? 9 and 2. 9 comes out of the radical as a 3. So we have to multiply it times the negative 6. So our final answer is negative 18 radical 2. When multiplying, just like adding and subtracting, you can only multiply if the indexes are the same. So here they're both an index of 3, so we're good. We can multiply our cube roots here. What's the coefficient on the second one here? A 1. So when we multiply the numbers in front, you're doing a 4 times a 1. So that would give us a 4. And then we have cube root of 16x to the 6th. Since we're multiplying, we add those exponents. So then I always like to check, is 16 a perfect cube? No, it's a perfect square, not a perfect cube. So we're going to have to do our little simplifying rule. What is a perfect cube that goes into 16? 8 and 2. Now is x to the 6th a perfect cube? Yes, I can divide 6 by 3, right? So x to the 6th is going to go in the first one. So when I take the cube root of 8, what do we get? 2. Divide your exponent, and you would not get a 3. You would get x squared. And then we still have after our cube root of 2. So our final answer, 4 times 2 would give us 8x squared cube root of 2. Example 3, what do you think we do? This goes back to our exponent rules that you guys loved oh so much. You have to square both parts of that. So you're squaring the 7, and you have to square the square root of 3. So what is 7 squared? 49. What happens when you square a square root? You guys remember? It just cancels. So this is going to be just a 3. So then all we have to do is, what's 49 times 3? 147. So whenever you see examples like these, and we're going to be doing quite a bit with those, there should be no radical in the end. When you square a radical, that sign is gone. All right, example 5. What do you think we have to do to that one? We got to do some distributing. So we got to start with a 3. 3 times 4 gives us a 12. 3 times negative radical 5 would be negative 3 radical 5, because remember there's a 1 out in front. So you would do the 3 times the 1. You can only multiply under the radical if both things are under the radical. So then we have to distribute the radical 5. So radical 5 times 4 would be 4 radical 5. And then radical 5 times negative radical 5 would be negative square root of 25. What is the square root of 25? 5. So this really is a 5. So now we'll combine our like terms. 12 minus 5 gives us a 7. We have the same radicands there, so negative 3 plus a 4 would give us a 1 radical 5. That's our final answer. 7 plus radical 5. For ones like number 5, a lot of you still keep messing this up, so you need to write it twice. So then you remember you need to distribute twice on this one. So we start with our 2 radical 3 times our 2 radical 3. give you 4 radical 9. And then 2 radical 3 times a 1 would give us a 2 radical 3. And then again, 1 times 2 radical 3. And then 1 times 1. Now we can clean one of these up here. Square root of 9, that's kind of like a little red light bulb going off in my head because that's a perfect square. Square root of 9 is 3, and when I multiply it times the 4, that's really a 12. So we'll change that to 12. Now when you're distributing out and you already know that's a 12, you don't have to write the 4 radical 9. You can just go ahead and write the 12 if you know it. So then 12 plus 1, 13. And then 2 radical 3 plus 2 radical 3 would give us 4 radical 3. That's going to be our final answer. All right, I'm going to give you a minute. I want you to try example number 6. Did anybody get 1 as their answer? Yes. So when I multiplied this out, 2 times 2 gave me my 4. And then 2 times radical 3 gave me my plus 2 radical 3. And then negative radical 3 times 2 gave me my negative 2 radical 3. And then negative radical 3 times radical 3 gave us a 3. It would have been the square root of 9, which turns into a 3. So then when I combine my like terms, 4 minus 3 gives me a 1. And then those cancel each other out. So we're just left with a 1. All right. Now we do have some division rules also. Division rules, kind of like what we were doing up on the front. If you can separate them and it works out, do that first. So like for this one, I would separate it into the square root of 121 over the square root of 9, which what is the square root of 121? 11. Square root of 9 is 3. So that one's done. When I look at example 2, though, those aren't perfect squares. So what you always want to try to do with division first is you always want to try to actually divide the numbers under the radical. Can we do 90 divided by 18? You get a 5. So we would have our 2 out in front still. 90 divided by 18 is 5. And then that one's done. Always try to actually divide them first. It's not always going to work out that way, but I would say about 80% of the time it does. So always try to actually divide. So times that it won't work are like these 2 examples down here. Can we divide 7 by 5? No, you're going to get a decimal. That's not going to work. So when we go back to the other rule, okay, I'm going to separate these, which neither of those are perfect squares. We have radical 7 over radical 5. We cannot leave it this way. You cannot leave a radical in the denominator. So what we do is we multiply it times whatever's in the denominator. So here was a radical 5, so we're going to multiply times radical 5 over radical 5. Reason we do that is, what would radical 5 over itself equal? A 1. So basically you're just multiplying it times a 1, but you're doing the step that we call rationalizing the denominator because you cannot leave that radical down there. So then we multiply our tops. Radical 5, or 7 times radical 5 gives us a radical 35. And then in the denominator, since you're doing that radical times itself, the radical sign just disappears and we're left with a 5, which we can have. Yes? No, I said radical 5 over radical 5 is a 1, so it's like we're multiplying times 1. So then that's going to be our final answer for that one. I can't simplify 35. If you could, you would. But in this one, we can't. No, because this 5 is no longer under a radical. This example up here, we could divide these two because they were under radicals. Okay, so example 2. I have a 2 over a radical 8. There's nothing we can do because this 2 is not under a radical. Only the 8 is, so we have to do the rationalizing the denominator. So I'm going to multiply times radical 8 over radical 8. So 2 times radical 8 gives us a 2 radical 8. Radical 8 times itself gives us an 8. Can we reduce our radical 8? Yes. What perfect square goes into 8? 4. So I've got to change this into radical 4 times radical 2. Which, let's see if you guys can do this in your head. Square root of 4 comes out as a what? 2. And when I multiply it times this 2, I get 4 radical 2 over 8. Can I reduce any of that? Yes. What can I divide 4 and 8 by? 4. So 4 divided by 4 would be a 1. 8 divided by 4 would be a 2. So I get radical 2 over 2. Or you could write 1 radical 2 over 2. That's perfectly fine. It can't be. All right. Rationalizing the denominator, if it's not just one radical like our other two, they were nice, you have to multiply times the conjugate. Now the conjugate, all that means is you take your denominator and you change the sign in the middle. Because again, our goal is you can't have a radical in the denominator, but this time we have a binomial denominator. So you got two things in your denominator. So for our first example, my conjugate would be 5 minus radical 3. You don't change the sign of the 5, just the sign in between the number and the radical. So we follow our same rules. I'm going to multiply across. I got to do 2 times my 5, which will give me a 10. 2 times my negative radical 3, which would give me a minus 2 radical 3. Then we have to distribute in our bottom. 5 times 5. 5 times negative radical 3. So I have 25 minus 5 radical 3 so far. And then radical 3 times 5. And radical 3 times negative radical 3. Now the reason why we use the conjugate, because as you see right here in the middle, what happens with these two terms? They cancel each other out. It gets rid of the radical, which is why you have to use the conjugate. So up top, I have a 10 minus 2 radical 3. In the bottom, I have 25 minus 3, which would be a 22. And then all three of my numbers outside the radical, can I reduce those all by the same thing? Yes. What can I divide them all by? 2. So 10 divided by 2 gives me 5. 2 divided by 2 gives me a 1. And 22 divided by 2 gives me 11. So that would be our final answer. So what would be our conjugate in example 2? 4 plus radical 5. You just change that sign in the middle and then you multiply. Lots of distributing in this one. 3 times 4, 3 times radical 5, 4 times radical 5, radical 5 times radical 5. So then I also multiply out your denominator. So up top, when you combine your like terms, 12 plus 5 gives us 17. 4 plus 3 gives us 7 radical 5 over, what's our denominator? 11. And then you cannot reduce your 17, your 7, and your 11 by the same number, so they stay the way they are.